sir. We'll keep it in mind.
Okay. Anyways, so what I will do today is I will be solving those questions also, which I was supposed to solve the previous week. So today, instead of doing two sums, we'll be doing four. Okay. So it would take around 1 hour of time. So let me start recording. And now let me start sharing my screen. You are able to see my screen, right? Everybody is able to
Yes,
see?
sir.
Okay. So let me share the question now. So today's first question would be this. Yeah. So these are 2014 GATE question which appeared in session 1. So a function has been given to you. Do you know the meaning of this statement? 0, infinity. Do you know the meaning of this statement? Anybody?
No, sir.
Okay, so this statement means ki the domain of the function, that is the arguments of this function of g would be from anything between 0 to infinity. Okay, and the output of the function would be also positive from 0 to infinity. Okay, so that means just a minute. So that means this value x can take any value from 0 to infinity, that is x is only positive. Okay, and the value of the function, that is g of x, can also be only positive. So that is what this statement means. This is a very important statement. This is a very important statement. I will point out why it is so important. So there is a function which has been given to you, x minus box of x, where box of x represents the integer part of x. Okay, this is another important point that you have to keep in mind. So the question has stated that box of x represents the integer part of x. Okay, so that is the largest integer which is less than or equal to x. Okay, so these are the actual mathematical definition is largest integer which is less than or equal to x. This is the actual mathematical definition of box of x. But the question has also stated it has stated it represents the integer part of x. Okay, so these are two important points. I will tell you whether it is okay or the essence of this line. Anyway, so what you need to do, you need to find the constant term in the Fourier series expansion of g of x. So what do you mean by constant term in Fourier series expansion? Anybody? What does the what is the question asking for? Hello, Navkirti?
Sir,
Yeah.
constant term means when we put x is equal to 0 at that point, the value
No,
of
no, no.
function.
I'm talking about Fourier series. So this function is going to give you a plot, and you need to find the constant term in Fourier series expansion. What does constant term in Fourier series expansion means? What is the Fourier series? First, tell me.
So we integrate the signal from
No, no. Tell me what is the
earlier.
Fourier series? What does Fourier series signify, or what is the Fourier series?
Sir, it represents a signal.
Any signal or
Sir, periodic signals.
periodic signals?
No.
Okay. Yes. So when there is a periodic signal, we can break it into several sinusoids and cosinusoids. Okay, and a DC term. Okay, so you may have seen that there is a DC term like A0 plus A1 cos omega t plus A2 sin omega t plus A3 cos 2 omega t plus A4 sin 2 omega t. This thing you have seen, right?
Yes, sir.
So the constant term means the DC part, that is the A0 which I am talking about. Just now I told the Fourier series, right? The A0 part or the DC part which doesn't have a sinusoidal component is called the constant term in the Fourier series. That is the DC part of the Fourier series is being asked for in the question. So what you need to do, you need to plot this g of x, and after that you need to find out what is the DC value of the signal. This is what you need to do in the question. So let me give you 3 minutes time to solve it. Okay, so what is the time now? Oh, so the screen is in a full screen mode. So it is 7 7. So up to 7:10 you will be getting time. So you solve this, then we'll be discussing the solution. Okay. Step by step we will be discussing. I will be pointing out the essence of the line that I just told. You can go ahead solving the question. Okay, the 3 minutes time that I had given is up. So anybody with the answer yet?
Sub point 5.
Yes, point 0.5 is correct. Okay. Anybody else? Okay, so let us discuss the solution. Okay. So let us first look at how the box function look like. Can you tell me how a box function looks like? How does the function box x look like? Anybody? Karthik, do you know?
No, sir.
Okay. Hari?
It consists of small lines, so like without touching the last integer, like
So how it
the
look
before
like?
integer like small lines, I think.
Small lines. Okay. How
On x
I mean you mean a linearly rising small line? What line you are talking about?
axis, inclined to x-axis.
Inclined to x-axis. Okay. Okay, right. So it looks like a staircase. Okay, so it looks like a staircase. I will show you how. Okay. So first let us understand what is the significance of this statement that when it has been told that the domain of the function f of x is positive, why is this statement so important? Okay, so first tell me the another part of the statement in the question that it gives the integer part of the argument. Is it always right or is it true for some condition? Is this statement, the statement written in green color, is this statement always correct?
Yes, sir, as given x is greater than 0.
Yeah, so if it is less than 0, it won't be correct. Okay, so how would this function would look like? So let us have a look. Okay, so I'm going step by step so that everyone can have a feel of what is actually happening. Okay, so So what does this blue line say? That box of x is the greatest integer less than or equal to x. So what is the greatest integer less than or equal to 0? That is 0. Okay. Now let us take a number 0.2. There are several integers which is less than 0.2. That is 0, -1, -2. All these integers are less than 0.2. But what is the greatest integer which is less than 0.2? That will be 0. So it is 0. Again, for 0.5, for 0.5 there are several integers which is less than 0.5. 0, -1, -2, all these are less than 0.5. But which is the greatest integer which is less than 0.5? That should be 0. Okay. Now let us take a point very close to 1. Very close to 1, let us take a point. So 0.999, something like this. So what would be the output of the function box of x? That would be 0, because the greatest integer which is less than this is 0, right? So we see that all the positive values, if x is a positive value, then it is giving the integer part of the argument, right? So 0.8, 0.5, 0.2, all these are argument of the function. And what are you getting? You are getting only the integer part of the argument. I have conducted the same exercise for another set of values, but one important point you must note is that if I take a point very close to 1 but less than 1, we are getting 0. However, if we take a point which is slightly greater than 1 or equal to 1, we are getting another value. So there is a discontinuity at this point. Do you understand this point? Now, Kirti, do you understand this point? Is everybody understanding what I am saying?
Yes, sir.
So tell me what would be this?
Can you repeat, sir?
Okay, so which one? The discontinuity part? Which one do you want me to repeat?
Yes, sir, that is discontinuity part.
So when do you say a function is discontinuous?
When at a point it suddenly rises or its value is
No,
infinity.
when the left hand side limit and the right hand side limit are not equal, right? If we are
Yes.
considering a point, say I have considered a point, say 1. So if I take the value of the function slightly less than 1, we see the value of the function, and we take another point which is slightly greater than 1 and see what is the value of the function. If these two values are not equal to the value of the function at that point, then the function is discontinuous. Now look at this point. So look at point that is x equal to 1. Look at point 1. Okay. So let us take a value very close to 1. So 0.99 I have said. But less than 1. Very close to 1 but less than 1. If it is less than 1, what we are getting? We are getting the output of the function is 0. Right? Right?
Yes,
Now,
sir.
yeah. So, and if I take a value which is slightly greater than 1, say 1.000001. So what would be the value?
1.
1, right? So these two values are not equal, right? These
Okay,
two.
sir.
So there is a discontinuity at these points. There will be discontinuity at 1, there will be discontinuity at 2, there will be discontinuity at 3. At all these integer values, you will find a discontinuity, right? So I have performed the same operation over here. So I have taken a point 1.2. There are several integers which are less than 1.2. 1 is less than 1.2, 0 is less than 1.2, -1 is less than 1.2. So which is the greatest integer which is less than 1.2? That is 1. Again, 1.5. So which is the greatest integer which is less than 1.5? That is 1. Similarly, you can, if you read, I'm reiterating this thing that I've just stated in this exercise. So similarly, I have taken a point very close to 2 but less than 2, that is 1.9999. So what is the output of the function? That is 1. Again, if we conduct the operation at x equal to 2, we are going to get 2. So there is a discontinuity at 2. Similarly, you will also find a discontinuity at 3, and I have illustrated that. See, so if you conduct the operation 2.2, there are several integers which is less than 2.2. 2 is less than 2.2, 1 is less than 2.2, 0 is less than 2.2. But the greatest integer which is less than 2.2 would be 2. So we are getting 2. Similarly, for 2.5, box of 2.5 will also give you 2. Box of 2.8 is also going to give you 2. And if you take a value very close to 3 but less than 3, you are going to get also a value of 2. And if you are going to take a value slightly greater than 3, you are going to get a value 3. So there is another discontinuity at 3. So you find discontinuities all these integer points. Okay. So having understood this, let us look at how the function would look like. So this is how the function is going to look like. From 0 to 1, the value is always 0. From 1 to 2, the value is always 1, because this is the greatest integer which is less than maybe this point. So 1.5 is this point. So what is the greatest integer less than 1.5? That is 1. So the value would be 1. Again, if you take 2.5, which is the greatest integer less than 2.5, that is 2. So the value is 2. If you take a point like this, that is 3.5, so which is the greatest integer which is less than 3.5, that is 3. So you're going to get a value like this, 3. So take a point 4.5, so what is the greatest integer? That is 4. So you're going to get a value like this. So this is how a box function would look like. Is this clear to everybody?
Yes, sir.
Yes, sir.
This is very much clear, right? Okay, so if this is clear, let me show you why there is a problem with the, not a problem, why is that statement very important? Why is this statement very important? See, if I take negative values of x, it has been exclusively told that the domain of the function is positive. What would happen if x is not positive, that is the domain is negative? What would happen? So if I take a point like this, say I'm taking a point minus 0.2. So what is the greatest integer which is less than minus 0.2? That is minus 1, right?
Yes, sir.
So the value is like this. So this is how the box function would look like, right? Right?
Yes, sir.
So just look at this. So minus 0.2, the integer part would be minus 0, right? That is 0. But what are you getting? You are getting minus 1, right? Did you understand?
Yes, sir.
So now the statement that they have said that box function is going to give you the integer part of the argument that you have that you are sending to the function, that is no longer true. The statement that box function is returning the integer part of the argument is no longer true if the domain is negative. Okay, if the value of x, if x assumes some negative value, this statement will no longer be true. See, minus 0.5, again, if you apply the same logic, it would be minus of 1. So if you again go for minus 0.8, it is again going to be minus 1. So the box function would look something like this, as you can see on the slide. I have conducted the same exercise for minus 2 to minus 1, and you can do it on your own. Say I have taken a point minus 1.2. So what is the greatest integer which is less than minus 1.2? That is minus of 2. Right? You agree with me on this point?
Yes, sir.
Yes, sir.
Are you getting, I mean, the concept behind this thing? What I am trying to convey over here? Are you getting the point?
Yes, sir.
So
Yes,
the
sir.
main thing that I'm trying to say that if this statement were not given in the question, then the question would have been wrong. And in 2017, there was a question, similar question, but the examiner didn't take this into account, as a result of which the question was wrong and marks has to be given to all. So this is a very important statement that has been given to us in the question. Okay, so this thing that you have to keep in mind. So okay, now we have understood how a box of x function would look like. Let us see how x minus box of x would look like. Okay, so x minus box of x, so 0 minus 0 would be 0. So 0.2 minus box of 0.2. Box of 0.2 is going to return a value 0. So 0.2 minus 0 is going to give you 0.2. 0.5 minus box of 0.5 is going to, box of 0.5 is going to return a value of 0. So 0.5 minus 0 is also going to give you 0.5. 0.8 minus box of 0.8 is going to give you return a value of 0. So you're going to get 0.8. So you see it is a linearly rising function, right? It's a linearly rising function, correct?
Yes, sir.
Yes, sir.
So you see, if x is a discontinuous function, my box of x is a discontinuous function and x is a continuous function, so x minus box of x would also be a discontinuous function, right? Because this term in the function contains discontinuity. Do you agree with me?
Yes, sir.
So let us look for a value of x which lies between 1 to 2. Again, I have conducted the same operation. 1.2 minus 1.2. So box of minus 1.2 is going to give you 1. So you're going to get only the fractional part, that is 0.2. 1.5 minus box of 1.5. Box of 1.5 is going to return a value of 1. So 1.5 minus 1 is going to return you 0.5. So you are getting the fractional part of the. Yes. Yes.
Sorry.
Okay,
Sir.
no problem. Okay, no problem. So box of x, when x is positive, is returning you the integer part of the argument. Whereas when you are subtracting that with the value of x, you are going to get only the fractional part. So you are getting the fractional part. Okay. However, there are discontinuities as x. As a result, if you conduct this operation, you will see that the function would look like this. Okay. Now, as the function is already known to us, what we see now over here is it is a periodic function. It is a periodic function. What is the periodicity of the function? It is unity, right? It is 1. Do you agree with me?
Yes, sir.
It is 1. Okay. So if it is so, then let us find the DC part, or the DC part of the signal means if I remove this DC part, then this function will be shifted by this amount, right? Do you understand the concept? So what does this DC part means? If I remove this A0, so if I remove this A0 from the function, this is going to shift vertically downwards, correct?
Okay, sir.
Did you understand what I am trying to say?
Yes, sir.
Now, Kirti?
Sir, you mean to say like average value or something?
A0 is the average value. So subtract the average value from the function. So the top of the function is 1. So say average value is 0.5. So you subtract 0.5 from 1, you are going to get 0.5, right? So it gets vertically down. The function gets vertically shifted downwards.
Yes, sir. Got it.
Got it. Okay. So this is what a DC part is. It just shifts this signal vertically. So you just need to find the DC part. That is what has been asked in the question. So how to find that DC part? That is 1 by t 0 to t g of x dx. That is, t is the period of the function, and this is the area under the function g of x in one period. So if you find the area of this shaded region, that is 1 by t into 1 by t, you have to do it. So 1 by t into shaded area would give you the DC part of the signal. So what is the shaded area? That is, the triangle is half, the base is unity, and the height is also unity. So half into 1 into 1, and the time period is also unity, that is 1. So A0 is half. So the correct answer is 0.5. So the correct answer is 0.5. Is the solution clear to everybody?
Yes, sir.
Is it clear to everybody? Hari, is it clear to
Yes,
you?
sir.
Yes, sir.
Okay. Okay. So now let us move to the next question. Okay. Okay. So clipper circuit has been given to you. Okay. So a clipper circuit has been given to you. You can see the circuit on the slide. Okay. So it has been asked, when, at what condition will the output voltage or the voltage across this would be clipped? That is, that would be at minus 1 volt or minus 2 volt. What must be the range of the input voltage so that the output voltage is taken across this, the output voltage is clipped. Okay, that is the question. So these are the options that has been given to you. Is the question clear to everybody? Hello? Navkirti, is the question clear to you?
Yes, sir.
So the output is taken across this 10 kilo ohm resistance, and the question is, for the output to be clipped, that is, for the output to be constant at minus 1 or minus 2 volt, what should be the range of the input voltage? Okay. So I will give you 3 minutes time to solve. So what is the time now? Let me just see. It is 7:27. At 7:30 I would be asking you the answer.
Sir, D option.
Okay. Navkirti says it is D. Does everybody agree with Navkirti?
Yes, sir.
So that is who is that?
Hari, sir.
Hari. Okay, Hari agrees with Navkirti. Hari and Navkirti says it is D. What about others? What do other people think?
Sir, option B,
Option B. Who is that?
Karthik.
Karthik. Karthik says it is B. Okay. Anybody else with the support of Karthik? Navkirti has 2 votes. One is herself and Hari, and Karthik has 1 vote. Anybody else? Okay. So let us understand what is the solution. So, Navkirti, why do you think the answer would be D? Why do you think so?
Sir, I just analyzed at which potential diode D1 will be on and D2 will be on, and clipper circuit means the upper portion will be clipped on a certain voltage. So D1 will work when the positive potential of D1 will be higher than 1 volt, that is 2 volts. So that is how I concluded it.
Okay, so you are saying okay. So now, so you are looking at the potential at this point, right? You are looking at the potential at this point. So one thing that you have overlooked, maybe you see whether this diode conducts or not, whether D1 or D2 conduct or not, current is always going to flow through this path. Do you see the path that I am showing by my cursor?
Yes, sir.
The current is always going to flow through this path even when D1 or D2 is conducting or not conducting. And if it is so, there is always going to be a potential drop across this 10 kilo ohm resistance. Correct?
Yes, sir.
And what you have considered is you have considered that the voltage at this point is VI.
Sir. Yes, sir.
So you have not considered the potential drop across this 10 kilo ohm resistance. Anyways, so I would go step by step and tell you how to solve it. So let us go step by step. So for those who haven't studied diode yet, I have briefly made this slide. So this is the circuit symbol for diode. This is called anode and this is the cathode. When the anode voltage is higher than the cathode voltage, then only the diode would be conducting. So when VA is greater than VK, anode voltage is greater than the cathode voltage, then only it is going to act as a short circuit. When anode voltage is less than V of K, then Vk is the cathode voltage, then it is going to act as a open circuit. Okay. So to identify whether a diode is conducting or not, or when the output is clipped or not clipped, we need to identify the voltages at anode and cathode to determine whether the diode is conducting or not. This is what our motive is. Now, this is just now what I've explained. You have the circuit as you can see on this slide. Whatever happens, whether D1 or D2 conducts or not, current is always going to flow through this path. Okay, you are always going to see a potential drop from this voltage Vi at this point. So to simplify it, what you can do is, can we redraw the circuit like this? Are these two circuits same? Navkirti, are these two
Yes, sir.
circuits same? They are same,
Yes, sir.
right? Yes. I've just moved this resistance from right side to this left side, but the potential at these points are still the same. So we can redraw the circuit like this. So if I can do it like this, so let us do a simple thing, that is use a Thevenin's theorem to see how the circuit would look from these terminals. From these terminals, how this circuit would look like. To find out, what I am doing is I am using Thevenin's theorem. So what is open circuit voltage across this? That is VI by 2, right? So there is 10 kilo ohm and 10 kilo ohm. So potential divided if you do, so it is VI by 2 across these two terminals. So open circuit voltage would be, or Thevenin's voltage would be VI by 2, correct?
Yes, sir.
Yes, sir.
And what would be the Thevenin resistance? You short this source. So 10 kilo ohm and 10 kilo ohm would appear in parallel. So what is the resistance? That is half of this resistance, correct? So it is 5 kilo
Yes,
ohm.
sir.
So it is 5 kilo ohm, correct? You agree with me?
Yes, sir.
So the circuit, Thevenin circuit would look similar to this, as you can see, correct? Okay. So let us move to the next step. So if I now redraw the circuit that I have just shown in this fashion, if you use the Thevenin's theorem for that, what this circuit now reduces to is this. This is a circuit after using the Thevenin's theorem, correct? So I have told you in the previous slide, what we need to identify is the potential at this point and potential at this point to find whether diode D1 or D2 is conducting or not. Okay. So in this sort of problems, what you do initially is you assume both the diodes are off. So if both the diodes are off, what is the potential at V1? If both the diodes are off,
V Thevenin, sir.
correct, because there is no voltage drop across RTH. No current is flowing. There is no path for the current to flow. As there is no path for the current to flow at this point and this point is electrically connected, then there is no potential drop across this because there is no current flowing through this. So the potential at V1 would be VI by 2. Now see, now for D1 to conduct, VI by 2 must be greater than minus of 1 volt. VI by 2 must be greater than minus of 1 volt. This is what I have written over here. VI by 2 must be greater than minus of 1 volt. Do you understand? Now, Kirti, where you have committed the mistake?
Yes, sir.
So VI has to be greater than minus of 2 volt. Okay. Similarly, for diode D2, what should be the condition? VI must be less than minus of 2 volt. This is what I have written. VI by 2, sorry. V1 must be less than minus of 2 volt. That is, VI by 2 must be less than minus of 2 volt, or VI must be less than minus of 4 volt. So the correct option is B. Okay. Now let us have a look how the waveform would look like. So what I have done is I have assumed that the input voltage is a sinusoidal voltage having a magnitude of 10. So what I do is I draw a straight line like this, indicated by red, which indicates that minus of 2 volt, and another line which is indicated by purple or pink color, which is minus of 4 volt. Okay. So in this region, which I have indicated by the first line, you see the first straight line on which my cursor is moving right now. So in this region, VI by 2 is always greater than minus of 1. So D1 will always be conducting in this region. What happens between this, in this small region, which I have indicated between these two lines on which my cursor is hovering right now? What happens in this small region? Both the diodes D1 and D2 are off. So if both the diodes D1 and D2 are off, what is the potential at this point? If both are off, it would be VI by 2, correct? So it would be VI by 2. So you see it is a plot of VI by 2. So that's why I have written 5 volt over here. It was VI was 10 volt. So I have written 5 volt over here. So between these two region, it would be following the input voltage by 2. Again, as I am moving away from this envelope formed by the red and the pink line, in this region, the VI by 2 is always less than minus of 2. That is, VTH is always less than minus of 2 volt. So it will again be clipped. D2 is on in this region. In this region, D2 would be on. Again, what will happen in between these two regions? Both D1 and D2 would be off. So the voltage would be, the output voltage would be following Vi by 2. Again, as I'm moving away from this envelope, it will again be, this relation will again be true, and it will again be clipped at minus of 1 volt. That is, D1 would be on. So how is the waveform looking like? The waveform looks like this. So it is clamped at minus of 1 volt. As soon as we are moving in this region formed by these two lines, it is following Vi by 2. Again, it is clamped at this voltage, that is minus of 2 volt. Again, in between this region, it is following the Vi by 2 voltage waveform that I have shown in the previous slide. And again, as I am moving away from the envelope, it is again clamped at minus of 1 volt. Is it clear to everybody?
Yes, sir.
Yes, sir.
Have you understood where you have committed the mistake, Nafkirti?
Sir.
So Rohit, it was Rohit, right? Who's Karthik? It was Karthik, right? Who said that it
Yes.
was B.
Yes, sir.
Okay, your answer was correct. Now let us go to the next sum, which I actually supposed to do in the previous session. Okay, so this is the sum that has been given to you. So there is a continuous time signal f of t, and a capital F of omega is the Fourier transform of it. This is a mathematical definition of a Fourier transform. And there is another function which has been given to you, that is g of t, which is integration of f of u e to the power minus j ut du, minus infinity to infinity is the limits of the integration. You need to find the relationship between f of t and g of t. 4 options are given. Gt is always proportional to f of t. Gt would be proportional to f of t if ft is an even function. G of t would be proportional to ft if ft is a sinusoidal function. Gt would never be proportional to f of t. I am giving you another 3 minutes to solve, and after that I would be asking you what answers you are getting. So it is 7:42. The 3 minutes is 7:45. I would be asking 7:45. Anybody with the answer yet? Your time is up.
Sir, B.
It is a even function. Why do you say it is B? Why do you say it is B, Navkirti?
Sir, I didn't solve properly. Just
Yeah, I mean, what logic makes you say that it is B?
sir, I just tried putting zero in sine and cos. That's all.
Okay, mathematically you have not. Okay, anybody else? Do you think Navkirti is right?
Maybe, sir.
What is your answer? What do you think?
If we take, sir, inverse Fourier transform, so
Yes.
maybe that option is right, I think.
Okay, so that is Karthik, right?
Yes, sir.
Okay, okay, okay. The correct option is B. It is okay. So let us see. Okay, so there is a definition of Fourier transform which has been given to you in the question itself. Okay, so now the definition of inverse Fourier transform is 1 by 2 pi integration of f of omega e to the power j omega t d omega. Okay, now what I have done is f of minus t I have written. Why I have done minus t? Because you see in the expression for g of t, in the expression for g of t, you have minus of j of ut over here. Okay, so what I did is f of minus of t I have written so that I can get a negative term over this e to the power term. I get a negative sign over here. That is why I have done f of minus t. If I do that, so let us multiply both sides by 2 pi. So you get 2 pi f of minus of t is equal to minus infinity to infinity f of omega e to the power minus of j omega t d omega. Right? Now let us compare these two expressions. If you compare these two expressions are exactly same. Correct? Only you see there's a variable you can always put u instead of omega. If you do that, then you see equation 1 and equation 2 are exactly the same. So g of t is equal to 2 pi f of minus t. But you are asked to find a relationship between g of t and f of t, not f of minus t. So when can we write f of t is equal to f of minus t? That can only happen when ft is a even function. So g of t is equal to 2 pi of f of t when ft is a even function. So we can say in such a case g of t is directly proportional to f of t, right? So the correct option is B. Do you agree with me?
Yes, sir.
Yes, sir.
Okay. So let us move over to the last sum, the last problem for today. Okay, so this is the last problem for today. So op-amp circuit has been given to you and you are asked to find the output voltage relationship in terms of V1 and V2. 3 minutes time I'm going to give you again. It is 7:49 now. So 7:50, 52 I'm going to ask you what answers you are getting. So time is up. How many of you have solved? What is the answer that you are getting? Nobody with the answer yet?
No, sir.
No, sir.
Hari?
Don't know, sir.
Anu? So have you? Are you guys not trying? How have you tried? Can you just tell me what approach you are taking?
Yes, sir.
Yes, tell me.
Sir, I just tried like out that output op amp, the R is grounded, so I didn't consider V1 only. I only considered V2, so that's how I was ending up as the answer, but I don't think so it's correct.
Why is there no reason to consider V1? I didn't get you. Anyways, let us discuss. Do you know anything about virtual shorting, virtual grounding? Have you heard these terms?
Yes,
I know
virtual
about
shorting.
something. Yes, sir. If two different voltage are applying and we are taking only one output voltage.
No, no,
I
no, no,
know.
no, no. So what is the potential at this point? Can you tell me what is the potential at this point?
So V2,
V2 is over here, right? V1, it is V1 over here. What is the potential at this point? At this point,
at this point V1.
V- at this point it should be V2. At this point it should be V1. Anyways, let me just tell you a few things before we apply that virtual grounding. Okay, let me just tell you a few stuff. Just give me a minute. Just give me a minute. Okay, because okay, okay, you can see my slides, right?
Yes, sir.
Okay, okay. So let us talk briefly about virtual shorting before we go ahead solving the sum. First, let us do that. So you see, for a ideal op amp, the gain A is infinity. Let us before doing that, you understand that this is a simplified model of op amp. The circuit that you see on the left hand side of the slide, it is a simplified circuit of an op amp. So what do you have? You have two terminals, V1 and V2. V2 is the non-inverting input terminal and V1 is the inverting input terminal. So what does this op amp does? It amplifies the difference in the voltages between these two terminals. So what is this? So you see that there is the kind of, you can see the what I mean the model that you are seeing on the slide. You can see that there is a kind of isolation over here, and you can, this is a model. Remember, this is a model. This is a mathematical model of the op amp. This is not what actually is there in op amp. This is a mathematical model of an op amp. So what we are trying to say is the output of the op amp is an amplified version of the difference between these two terminals. So V out is equal to A into V2 minus V1. So V1 is the potential which is applied at this terminal, that is the inverting terminal, and V2 is the potential that is being applied at the non-inverting terminal. Plus Vsat minus Vsat are the power supplies that we have supplied to the IC, op amp IC 741 op amp IC that you see. You need to supply VCC and ground. You have seen, you will find that there are two terminals like this where we apply plus voltage, minus voltage, or ground, whatever is the data, whatever the data sheet says. You have to apply this voltage from outside. Okay, and this is the output that you are going to get. This is a kind of a small signal modeling, simplified small signal modeling. Okay, so if V out is A into V2 minus V1. So V2 minus V1 can be given as V out divided by A. Right? Do you agree so far? Do you agree with me so far?
Yes, sir.
So I am saying that op amp has an infinite gain, then this A is tending to infinity. That means V2 minus V1 tends to 0. That means the difference between V2 and V1 is tending to 0, and V1 is almost equal to V2. Even if there is no actual shorting between these two terminals, V1 and V2, the voltages at these 2 points is same. But is this concept, or is this virtual sorting phenomena true for all conditions? When is it true? When is it true? Do you know when it is true? When can we apply this concept of virtual sorting?
Sir, when we are taking a different input and we are putting into the together and we are taking one output only.
Can you say from the characteristics? This is the input of transfer characteristics of an op amp. Can you say in which region it would be true? Would it be true in the saturation region or the linear region? Which region would be true?
No, sir, I don't know about that.
See, the x-axis V difference, right? V diff. V diff is
Yes,
what?
sir.
Okay. So when I'm saying that V out equal to A into V diff, that means we are talking about the linear region.
Yes, sir.
Okay. So this relation itself is true when you are operating in this linear region,
In
correct?
region. Okay, sir.
But this gain, I am saying it is infinity. So this slope would be far more steeper. It would be very steep. It would be like this. It would be parallel to y-axis. Then only it is going to be steep, right? Yes. Do you agree with me?
Yes, sir.
What does
Yes,
a
sir.
equal to infinity means? That means the slope is infinity. That means it is almost a vertical line, correct?
Yes, sir.
Okay, so this curve is not drawn to the scale. This is just for your understanding. You have to make sure whenever you are applying this concept in any problem while solving questions, you have to make sure that the op amp is operating in the linear region. You have to check that whether the op amp is operating in a linear region or not. That is, it is not acting as a comparator, or there is no positive feedback given to it, or the output voltage is not going beyond VSAT or plus VSAT or minus VSAT. These are things that you need to check, okay, before you apply the virtual sorting concept. Another property that you have to keep in mind for solving the sum is the input impedance of an op amp is very high, almost tends to infinity. For ideal op amp, it is tending to infinity. So there is no current which is flowing from this terminal to this terminal. That is ID1 and ID2 has to be equal to 0. Do you agree with me?
Yes, sir.
So if the input impedance is infinity, that means no current is flowing through the input terminals into the device. So I have written ID1. D refers to device current. ID1. Okay. Another point that you have to keep in mind, that Z out, the output impedance is tending to 0. If output impedance is not tending to 0, then there will be a voltage drop across this, and the output voltage will be lesser than this voltage gain, A into VDIF, that I am saying. It would be lesser than VDIF if there is a high output impedance. So it is desirable that Z out is very low, and for ideal it is almost tending to 0. So you get V out equal to A into VDIF. Do you agree with me on this point?
Yes, sir.
So what in a practical op amp or a IC that you see, what is the input impedance? Do you have any idea? What is the practical value? So these are mathematical terms, infinity. What is the range of this, range of this input impedance? Any idea?
Sir, in kilo ohms.
No, it is in mega ohms. So that is why when you are attaching kilo ohms like this, when you are attaching kilo ohms of resistance like this, then you can, just a minute. By class পরে কথা বলছি. So So when there is when this resistance are in kilo ohms, that is much lower than mega ohm resistance that is existing between these two terminals, imaginary resistance that is existing between these two terminals. So we can assume that no current is flowing through this. So if you attach a resistance of mega ohms or so, then you cannot neglect the input bias current which is flowing into the device. In such a case, also you cannot make this assumption. However, there is no question based on all these things in gate. But in the previous slide that I have just told you, that you need to make sure that it is not that is operating in linear region before applying that virtual shorting concept. That has appeared several times. You must keep that in mind. This is just a practical aspect that I pointed out that may be useful if you go ahead for higher studies or your PhD or maybe masters or something like that. Anyway, so now let us, having understood the properties of ideal op amp, just let us look at how to solve the sum. Okay, so we have already told you if you see there is no VSAT or something or minus VSAT attached in the circuit. That means the op amps that we are using are infinite and there is no saturation or something. If that is so, it is always operating in linear region, and then you can say that V2 is the potential at this point is same as potential at point A. Similarly, you can say the potential at this V1 is same as potential at point B. Correct? Up to this much, do you agree with me?
Yes, sir.
Okay. Now what I have done is, I already know that the input impedance offered by the op amp is infinite. So no current can flow through this path, or this path, or through this path, or through this path. No current can flow through this path. So the only path that through which current can flow is this, right? This is the path through which the current can flow. That will be indicated by the red arrow on this slide, right? You agree with me?
Yes, sir.
Okay. Okay, if that is the case, then we already know the potential at point B from virtual shorting concept, that is V1. We know the potential at A, that is V2, by the concept of virtual shorting. Now we want to find the expression for the current I which is flowing through this path in terms of V1 and V2. So I have assumed the direction like this. So I am saying that the current is flowing from point B to point A. The current always flows from higher potential to a lower potential. So I is equal to VB. B is at a higher potential because current is flowing in this direction, and A is at a lower potential. So VB minus VA divided by 2R. That is the resistance of this path. So VB, I have already told you, VB is equal to V1 and VA equal to V2. So I is equal to V1 minus V2 divided by 2R. This much you are agreeing with me, right?
Yes, sir.
Okay. Now, so potential at this point is known to me. What I am interested to find is the potential at this point C and point D. Because once I can find the potential at these 2 points in terms of V1 or V2, then this becomes a simple op amp circuit, simple single op amp circuit. We can just use the formulas that we already know and you can find the output voltage. So our main interest is to find the potential at point C and point D. So what is the potential at point C? That is potential at point A minus potential drop across this resistance, because as I've already told, current flows from higher potential to a lower potential. As the current is flowing from A to point C must be at a lower potential, and by how much it should be lower than point A? There is a potential drop across this resistance R. So what I have done, we have already known the potential at point A is V2. I have written V2 minus of I into R, because I into R is the potential drop across this resistance R. Correct? Agree with me?
Yes, sir.
So now I have replaced I with the corresponding expression that we have derived in terms of V1, V2. If you do the operation, you are going to get an expression like this: 3 by 2 into V2 minus V1 by V1 by 2. Similarly, we can also find the potential at point D. How we are going to do that? We know the potential at B. We have assumed the current is flowing from D to point B. If that is so, D must be at a higher potential because the current is flowing from higher potential to a lower potential. So point B is at a potential V1 and point D is at a higher potential, so plus. By how much it should be higher? That is the potential drop across this resistance. It is I into R. So v1 plus, I have again replaced I with the corresponding expression in terms of v1 and v2, and then we get a value like this. So now once we have found C, potential at C and potential at D in terms of v1 v2, now we are going to apply superposition. So when you have a potential at point D and you assume that potential at C is 0 for applying superposition, you say that C is at a 0 potential, you have applied only this potential Vd to this op-amp circuit that you just see, only single stage, forget about this stage, only single stage op-amp you think of. Okay, if that is the case, you have connected a potential V of D to this op-amp, the C point is grounded. In such a case, what should be the expression for the output voltage? You have applied a potential Vd at this positive terminal, as you can see, through this potential divider network, and point C is assumed to be grounded. What would be the output voltage in such a case? Yes, Karthik. Do you know what is the expression for that?
No, sir.
So if you are applying, so if you know the potential at this point, you'll follow my cursor. You can see my cursor.
Yes, sir.
If you know the potential at this point, and if you have a circuit like this with C grounded, the expression for the output voltage is 1 plus RF, that is the feedback resistance RF, divided by this resistance R. But you need to know the potential at this point. You know the potential at this point, right? So if I know the potential at this point and I know there is no current flowing into the device, so this is acting as a potential divider. The potential at this point would be Vd by 2. Do you agree with me?
Yes, sir.
So if it is Vd by 2, the output voltage only for the potential Vd would be 1 plus Rf, that is R over here, 1 plus Rf divided by this resistance, that is R. So 1 plus R by R. So that is 2 into Vd by 2. So it is only Vd. Correct? Agree with me?
Yes, sir.
So now, as we're applying superposition, now let us assume that D is grounded or D is 0. D is at a 0 potential. We have applied potential V of C at this point, at point C. So what would be the expression for the output voltage when only C is, VC is the potential at point C. Only when VC is applied with D grounded, what would be the output of the op-amp circuit? Navkirti?
So as written, we see RF divided by R.
Correct. So minus of, not VC, it is minus of, because it is at a non-inverting terminal. The input that I'm talking about, VC, that is at a inverting terminal. So if it is at an inverting terminal, it will be minus of RF divided by R into this potential. So VC into minus of RF by R. RF is R over here. So what expression we are getting is VD minus of VC. Okay. So now we already have got the expression for VD and VC in terms of V1, V2. You subtract this two expression. What you are going to get is 2 into V1 minus V2. Correct?
Yes, sir.
Okay, so you agree with me till this point?
Yes, sir.
Okay, so
Yes,
the correct option is C. Okay, that was the last question to be solved for the day. I think we will put an end to the session now. So I hope you like the session. You like solving the sums. Are you guys practicing, or how are you guys doing?
So giving test series.
Okay, good.
Yes, sir.
Okay. So your time is coming. So it is already December. Best of luck. I hope you do very good, and I will be seeing you some of you at IISc. Very nice conducting sessions. Okay, we would meet again on Friday. Till then,
Yes, sir.
enjoy your weekends. Thank you.
Thank you, sir.
Yes, sir. Thank you, sir.
Thank you.